Hello, and thank you for joining us. Welcome to this webinar event, introducing distributions of sample proportions and sample means. Now, this is one of many such webinar-based professional development events brought to you by Texas Instruments Australia as part of our ongoing support for teachers in the classroom. Your presenters this evening are Peter Flynn and Frank Moyer. Your host is myself, Brian Lannon. And you are lucky that we have both our presenters this evening as senior national trainers from the Teachers Teaching with Technology program. Good evening, Peter.
Good evening.
And Frank Moyer from Frankston. Good evening, Frank.
G'day.
Both these presenters extensive teaching and consultancy and mentoring experience and both have passions with TI technology application. Frank particularly looking at the use of rich tasks and investigative approaches, and Peter particularly looking at that with its impact on assessment. First off the rank is Frank. I shall send us across to Frank.
Okay, so good evening and welcome everyone. First of all, I'm going to be talking about sample proportions and sampling generally. The reason that we often take samples is in order to estimate characteristics of the whole population based on sample results. Now, typically, the characteristic that we might be interested in might be a non-numerical one, such as the proportion of brown eggs produced in an egg farm based on random samples. And that would be an example of statistical inference for sample proportions, which is what I'll be talking about. Alternatively, it might be a numerical characteristic, such as the mean weight of eggs produced. So that would be an example of statistical inference for sample means, which is what Peter will be talking about. All right, so sample proportions. Now, the beauty of this topic is that you can use real data. You could use, for example, data from Newspoll, or in this particular case, this is one that I came across when I was in the US earlier this year. The headline said, about half of Americans say teachers need more support to handle discipline issues. So this was based on a survey conducted by the respected Gallup organisation in February this year, based on a random sample of 1,000 adults. So in this case, some notation, N equals 1,000. So the response of teachers need more support, we'll call that a success. So 535 successes, and we'll let the random variable x be the count of the successes, and small x be the values that the random variable can take. So in this case, lowercase x 535. Now, the proportion, the sample proportion based on this survey, we give that the symbol p hat. So the true population proportion, which we don't know, is p. P hat is the proportion from the sample. So in this case, it's 0.535. But how reliable is this statistic? Because after all, that was a sample of 1,000 out of an adult population in the US of 250 million. So in order to answer that question, we need to understand how sampling behaves. And in statistical inference, we see the trustworthiness of a procedure by seeing what happens if we repeat it many times. And that leads directly to the concept of the sampling distribution, which is what Peter and I will be talking about. So we need to simulate repeated random sample to understand how sampling behaves, and the dynamic features of TI-Nspire are absolutely ideal for doing this. So in this case, the first simulation, we're going to assume that the true population proportion is 0.5. Now, normally, we wouldn't know what the true population proportion is, otherwise we wouldn't have to carry out the survey. But in order to help us understand how sampling behaves, we're going to assume the value of the true population proportion. And we're going to take repeated random samples of size 20. Okay, so the number of successes is binomially distributed with n equal 20 and p equal to 0.5. So the syntax we use is random binomial NP, the number of trials. Of course, if students are doing this on their handhelds, should also do a random seed to make sure that they don't all get the same results. Unless you want them all to get the same results, in which case you put the same seed number. All right, so we're going to build up a model of the sampling distribution, one survey result at a time. So the architecture of this page, in a text box, I've got the random binomial, sorry, not in a text box, in a maths box, in a notes page in the top half, top third, I've got the number of successes, which are generated randomly, so that's from number of successes from a random sample, and the corresponding proportion. So every time I hit enter, I select a different sample. And what we can see down the bottom here is that the number of successes and the corresponding sample proportion vary from sample to sample. So not only is the number of successes a random variable, but the sample proportion, p hash, also is a random variable. So the actual count, the actual proportion in a single sample is lowercase p hat. The random variable is capital P hat. And I think that's a subtle distinction that students need to get their head around. And each value of lowercase p hat is a point estimate of the true population proportion. So we're going to try and come up with the distribution of more support responses from random samples, and we're going to do it by taking one survey at a time. So I've set up this page, which is run by a program at the end of problem 3, and each time I draw, I'll draw one sample. So that's a sample of size 20, and as it turns out, it's 0.5. Oh, that was, I can reset, start again. Okay, so 0.45. I'll choose another sample, 0.45 again, 0.65. Now, over here, I've got the mean of those three samples, and here, the true population proportion. And as I select more samples, I can see that the mean of the sample proportion jumps around a bit. Okay, so I'm up to getting more and more samples. I'll speed this up. And students can see a distribution emerge. And I think that it is important that students do see that appearing one sample at a time, because I'll just jump back to here. I could have gone to here and just changed that to 200, and bingo, in one fell swoop, I get something that approximates the sample distribution. But I don't think that that is as meaningful to students as seeing it happen dynamically. So my advice would be, in the first instance, one, build that up, one survey result at a time. Okay. So that's the results in using a dot plot, and that's exactly the same data, except this time it's as a histogram. All right. So the distribution of of p hat is the distribution of values of the sample proportion for all possible samples of the same size taken from the same population. So in this simulation, we're not showing all possible samples, we're showing 200 random samples. But it does provide an approximation that allows us to see what the sampling distribution would look like if we had a lot more. Okay, now the other thing that was interesting was, I'll just jump back to here, that even though the mean of all of those values jumped around, as I had more and more and more samples, or sample results, we saw that the mean of all of those results converged towards the true population proportion. In fact, in this particular, for those 200, the mean of those 200 results is 0.5075, very close to the true population proportion of 0.5. So, is that a coincidence? Well, from the simulation, we observe that it tends towards the true value p. Is it consistent with the algebra? Well, the algebra is actually not all that complicated. So, p hat is x over n. We know that x is binomially distributed, so the expected value of x is np. The n's cancel, and sure enough, the expected value of p hat equals p, the true population proportion, which is really fortunate because it means that the p hat is what's known as an unbiased estimator. Okay, so that there is just the program that drives that simulation, and I'm not much of a programmer, so if you can do programming, you might be able to improve on that. So this will all be available for download as from probably tomorrow or the day after. So you can see how it has been set up, so you can use it as is or modify it to your needs. Okay, so the third simulation. So this time, we're going to the same sort of thing again, repeated random samples, except instead of just being limited to samples of size 20, you can choose your own sample size. So, for example, I might do a sample size of 90. So I'm going to do repeated random samples of size 90. So I'll take another sample and another, and build up picture. And once again, we see that the mean of all of those values converges to 0.5, true population proportion. The other thing that seems to be a bit different is that it doesn't seem to deviate as much from 0.5 as in the previous one. So that might be something worth investigating. Okay. So the standard deviation, once again, we can do some algebra. We know that the variance of x is np1 minus p. And the algebra comes out pretty simply, and the standard deviation is the square root of p1 minus p over n. And the significant thing is that the n is in the denominator. Okay, so that's the program driving us. Now, to investigate the effect of changing the sample size, I'm going to speed things up a bit this time. Now that students have seen the approximation to the sampling distribution built up one survey at a time, we can now do 200 at a time. So this time I'm using the command binomial, random binomial n. A slider is going to control the value of n, 0.5 per p, and I am going to do 200 in one fell swoop this time. Okay, so I start off, so this is 200 samples of size 20 and 200, the results of 200 samples of size 30, 40, 50, and so on. And yes, the thing that is most obvious is that as n increases, the spread decreases. And also, it becomes more symmetrical as the value of n increases. All right? So, from the simulation, students will hopefully see that for a given value of p, the spread and symmetry of the sampling distribution depends on the sample size n. So the spread decreases as the sample size increases, and the symmetry also increases with sample size. And it shouldn't be, the change in spread shouldn't be surprising because for the standard deviation, the value of n is in the denominator. As n approaches infinity, the standard deviation approaches 0. Okay, now, other features of the sampling distribution that we can get from this simulation. So, can we come up with a probability model that fits the histogram and dot plot? Right, so I'll go back to this page here. I'd stick with size 20 to start with. So that looks fairly symmetrical. So we know that the normal distribution is a symmetrical distribution, so I wonder how well that fits. Well, one way that you can get a visual representation of the normal curve on top of that is if you go to, once you've got the histogram, menu, analyze, and show normal PDF, and you can see the normal PDF there. It's actually not too bad. And I'll redraw, so this is 200 new samples, and another 200, and another. So, generally speaking, it's pretty good. Now, from the dot plot, you can test the approximate normality in a different way. So, from the dot plot, you can change the two ways you can do this. You can go through the menu and you can change the plot type, or you can just click on it and do a right mouse click if you're using the software, or control menu if you're using the handheld, and change that to a normal probability plot. Now, what the normal probability plot shows is the expected value if the data was exactly normally distributed against the actual value. So if it was a perfect normal distribution, then all of those points would be on the line. Now, we see that not all the points are on the line, but it's actually not too bad. So we can see that the normal distribution is a reasonable model for the sampling distribution. Okay. And
pretty handy one, Frank, that putting up the normal distribution on top of it. I really like that.
Yeah, that's right. I mean, for students, that's the more convincing one. I mean, showing the line of best fit is probably more for teachers than for students. I think that having the bell curve on top is probably the one that's more useful for students. Okay, this is another simulation. So this time I've got a slide, a notes page, and this is to illustrate that you can insert sliders in notes pages, and I've got the standard deviation here in a maths box in the notes page, and I can change the value of n, and one of the things that you can see is that as the value of n increases, the standard deviation decreases and in fact approaches 0. So that's just a different way of students seeing, just basically a different representation. So they've got graphical, they've got numeric representation of the same idea.
It's the first time I've seen a slider in a notes page. Is that a new thing you say, Frank?
No, I don't think it's new. I think sliders have been in notes pages for several years, haven't they?
You're just the guy who's smart enough to utilise it. Very good.
Okay, so I think this is the last simulation. So the effect of the population proportion on the sampling distribution. So we've seen the effect of changing the sample size while keeping the population proportion the same. What if the population proportion changes? All right, so we'll start with a population proportion of 0.5, sample size of 10, very small sample size, and I'll increase the population proportion. Okay, and then I'll decrease the population proportion. So with this sample size 10 at least, we can see that the spread becomes less. So the spread is greatest when the population proportion is 0.5, and it's smallest, the spread is least, when P is either close to 0 or close to 1. And we also see that it becomes less symmetrical. And although if I increase the value of n, we see that a little bit more symmetrical, but even so, the spread is less. So now I've got a sample size of 40, and you see the similar sort of effect, that the spread is greatest when P is 0.5, and it's also most symmetrical then. All right. So when you get this page, one of the other things you'll be able to guess, I'm going through this quickly so I don't want to eat into Peter's time, but one of the other things you can do is have a look at the actual statistics. So for this distribution here, you've got the value of P, the value of N, the standard deviation, and all the other statistics. So it's just one variable, stats, and you've got all the results there. All right, so what we can conclude from that is that for a given sample size, the spread and symmetry of the sampling distribution of P hat depends on the population proportion P, with it being greatest when P is 0.5. And it also becomes more symmetric closer to 0.5 and least symmetric the closer it is to either 0 or 1. Okay, so one of the key features is that the approximate normality of the sampling distribution depends on N, and it also depends on P. Okay, so we see that the symmetry and all of that sort of stuff changes, but both N and P can change that. So for what values is it reasonable to use the normal distribution to model the sampling distribution of P hat? And if you look at very old textbooks, I used to quote that N times P had to be at least 5, and N times P times 1 minus P had to be at least 5 as well. Now, that's gone out the window. Many statisticians today now say that it should be at least 10 successes and at least 10 failures. In fact, other statisticians say, no, even that is too generous. It should be at least 15 successes and at least 15 failures. So no clear indication as to when you can use the normal distribution, but as a good model, but at least is probably what the majority of statisticians believe today. All right, so that brings to an end my section on the sample proportions, and I'll hand over to Peter, who can talk about sample means.
Thanks, Frank. Yeah, very extensive there. Since we highlighted the slider in the notes page, someone did ask how you get that. It's actually from the menu in Insert, so the same area where you would insert a math box. Insert slider is the 5th option there, and it is. I'm running 4.5, and I can see that it's on. It's on the software that I've got there. So I'm not sure when that came in initially. Just a reminder to everyone that you do get a copy of these files. Frank did mention it. We distribute that if you've registered for the event in an email, or otherwise it's available to download from the webinar section of the Texas Instruments Australia website. Along with, would you believe, a link to a recording, which is happening right now, a recording of the entire event. So thank you again, Frank. We've switched across to Peter.
Brian, can you see my screen?
We can very well, thank you.
And you can hear me clearly?
We can do that as well.
Excellent. Good evening, everybody. Well done, Frank. That was fantastic. And what I'll do now is just have a brief look at sampling distribution of sample means, mostly from the point of view of simulation. I don't think I've got enough time to go into theoretical considerations, but I think when you teach this topic, it's extremely important to utilise the technology and exploit it, just like Frank did, to illustrate properties of the sampling distributions, and in particular, what happens to a sampling distribution when you change the sample size. I think it's a mistake to teach this from a textbook in a static environment in a very theoretical way. I think it's really important that students have a conceptual basis for such phenomena like sampling distributions of sample proportions, as Frank did, and also sampling distribution of sample means. So I think it's absolutely crucial that you use TI-Nspire technology here to develop simulations, show the simulations with the students, and then ask them questions and have a really nice discourse with them so that they end up with a good conceptual understanding of what's going on. And I think another reason for doing that as well is if you teach it in a very static theoretical way, the notation can be quite overbearing, and Frank made some really good remarks there about the importance of the notation and subtleties that students may miss. So in actually taking part in the simulations, you do offer the students an opportunity to get a grasp on the various notations. In particular, that a random variable is denoted by an uppercase letter, and in this case, when we're talking about sample means, it's X bar, and point estimates will be little X bar, just as we had capital P hat and P hat and little p hat in the sample proportions that Frank was talking about. So there on the first page, it's a notes page, and there's my name and email address if you wanted to contact me. Moving to the next page, it's really important, I think, to seed the calculator or the handheld, because what can happen is if at the start of the year and you're teaching a class and all the students get their calculators out and they haven't been used before, and just say you wanted to do some sort of simulation, you wanted to generate some random numbers, what happens is that the handheld or the calculator is on factory settings, and so in effect every single calculator or handheld is set the same way. So if you performed some sort of simulation like rolling a die, every single student in the class will get the same result. And what happens there is you end up destroying their notion of randomness forever. So what you do is you seed the calculator, and that is, now I'm in a notes application here, so it's slightly different to the calculator application, but if you go menu, number 6 for calculations, and then 5 for probability, and then 4 for random, number 6 is seed, so random seed. And what it does is when you enter a number such as your mobile phone number without the leading 0, what it does is it takes your handheld to a different part of the pseudo-random number list as compared to all the other handhelds in the room, and it ends up just running off on its own accord. So I think it's really important before you do any simulation to use the ranseed command to seed your calculator so that you don't have students in the class getting the same results. It would be dangerous in a large class if you said to students, put in your birthday, because in a class of 23, for example, there's about a 50% chance of at least 2 people in the class sharing the birthday. So mobile phone number without the leading 0 would be fine. So this page here is where you would enter that, press enter, and therefore you're away. So the cornerstone command, Frank, for his sample proportions, was the random binomial command. And when we're talking about the distribution of sample means, the random normal command is the one that we use. And again, this is a notes page. The syntax is randnorm mu, which is the population mean, sigma, the population standard deviation, and n is the sample size. And so in this math box here, well, actually, first of all, if you wanted to find the randnorm command, again, it's in a notes application. It's menu, 6 for calculations, 5 for probability, 4 for random, and then you'll have number 4 there, the random normal command. So just press escape. We have a math box here, and a math box is inserted by pressing Control M into a notes page. And we've just typed in there randnorm. So the mean is 30, and the standard deviation is 7, and the sample size is 5. And you can ask students, particularly in Year 12, do they know of any situations where you've got a normal distribution with a mean of 30 and a standard deviation of 7, and in fact they should know that in fact that's a situation for a study score that they will get when they at the end of the year for a particular subject. And when you press enter, what we see there is 5 random values drawn from that population mean of 30 and standard deviation of 7. And you can in there press enter and it will update. So that's the strength of using math box in a notes application. The notes application, is one of the one of the least known applications, but I think it's the most powerful. So when I do a lot of my calculations on Inspire, I hardly ever use the calculator application. I use the notes application. Down here, we have another math box, which was introduced by pressing Control M. And what I've done here is I've assigned study score. And you can see that study score has an underscore between study and score. Now, underscore is accessed by pressing Control and then space. And notice here you've got the colon equals. That's the assign command, and that's accessed by pressing Control and then the symbols template on the keypad. And what it's equal to here, INT stands for the integer part. So it's just taking the random number, and let's just deal with the, let's have the integer part of the number and not worry about the decimal equivalent. And integer is found by pressing menu, 6 for calculations, 2 for number, 8 for number tools, and then number 2 for integer part. So that's how you would find INT. Of course, the quickest way is just to type in INT. So we've got the integer part of rand norm 37,100. So we've got a mean of 30, a standard deviation of 7. So it's a population mean of 30, a population standard deviation of 7, and we've got 100 study scores. And what you can do is you can illustrate this nice property that about 95% of those study scores should lie between the mean minus 2 standard deviations and the mean plus 2 standard deviations. That's shown in this last math box here, where I've used the COUNTIF command. So we want to COUNTIF study score that lies between 16 and 44. That question mark you see there is acting as a placeholder. And so in the current set of data, we've got 98 values lying between 16 and 44. If you press enter, so what I will do there is press enter here. And therefore, in this instance, you get 95 of the values, 96 of the values, 97 of the values, 93 of the values. So this is illustrating random fluctuations, and it gives the students a handle upon this idea of an approximate 95% confidence interval. I think that that's a nice demonstration to show the students as we build into this idea of distribution of sample means. And I think this is what Frank did as well. Now, we've both got 25 minutes, so it's a bit of a potted history about how we actually teach this. And to do it properly, you don't do it in 25 minutes, you do it over a couple of lessons. But I think one thing that you do is you build things up slowly, and I think that that's what one of the strengths of Frank's presentation there. You don't want to cut to the chase, you want to build up slowly. So here what we're doing is we're just starting on a journey, and we're just generating one random sample of size 10. So we're considering a random variable, capital X, and it's assumed to be normally distributed with a mean of 100 and a standard deviation of 15 from a particular population. And we just want to get the students used to simulating the drawing of a random sample of size 10 from this population. Now, the last comment on this notes page is that in a spreadsheet, which you're going to see on the next page, pressing Control R generates another sample of size 10. So Control R stands for recalculate. It could also be thought of refresh, and it just offers another calculation, or in this instance, another random sample of size 10. So the next page is quite busy. It's a split page. The left-hand side is the list and spreadsheet application, and the right-hand side is a notes application. So what I've got here is the column A heading cell is X, which may not be the best one heading to use, because remember that further on in the spreadsheet there is a column X, and so the TI-Nspire will ask you, whether X is a column variable or not. And so I'd advise you probably, I'm going to keep it as X, but XX, for example, would stop that situation occurring. Here we've got the formula cell, and this is where we're putting in the rand norm command, and the syntax here again is mu, sigma, n. But the nice thing about this page is that over here on the right hand side in the notes application, we've got a slider which is controlling the value of n. So at the moment we've got a sample size of 10, and that slider we can change the sample size. The population mean has also been assigned to be 100. The population standard deviation has been assigned to be 15. And what's happened in these last two math boxes is we have a calculation for the sample mean and also the sample standard deviation. So if I open up the math box there, I've assigned S_mean to be the mean of X. So it's the, it's the mean of those 10 values that you can see in column A of the spreadsheet. And that comes out in this instance to be 101.457. And the standard deviation, sample standard deviation, in this instance is 12.3897, and that's also from using the formula. Now you can see those two numbers, 101.457 and 12.3897. You can also see those in the spreadsheet. So here are our 10 values which have been drawn from this population of mean 100 and standard deviation 15. So it's nice for the students to see the fluctuation there. So we've got a 90, 114, a 98. Okay, so that's quite nice. And what I've done here is in cell B1, I've entered in equals mu, and so that's the population mean, so that's anchored at 100. Here, that's I've typed in equals S_mean, and that's the sample mean, and similarly S, that's underscore SD, that's the sample standard deviation. So it's nice to have a tabular representation, but it's also even better to have a graphical representation. So this is a data and statistics application, and when Frank was doing his sample proportions, he really used this environment extremely well. What you see there, these are the 10 values that have been drawn from the population, and we have two vertical lines. One is fixed, and it's the population mean mu, which is 100, and the second one dances around. It's the sample mean, and it's 101.457. And so what we would be expecting is, by changing the sample size, or even by changing the sample, what would happen is that the sample mean would be fluctuating or dancing around the population mean. So if we went back to page 1.6, and you can either do Control R or make contact with the formula cell here, open it up and press Enter. Go to the next page there, and notice here that the sample mean is, in this instance, a lot closer to the population mean. And so just getting the students into this idea of random fluctuations, I think, is really important. And we've got a clicker here which we can use to increase the sample size. So we expect to see more dots appear and you'll also see the sample mean, you know, as I said, dancing around the population mean. So that's a lovely demo to show the students. The other nice thing about this page is I have a reset button. So by clicking on there, it takes you back to a sample size of 10. And what's really interesting, if we look here, with a population mean of 100, we've got a 69.04 here as one of our values, and similarly a 125.615. So it does fluctuate quite a bit. Here is an example of the reset program. Normally what you would do when working with the students is you would hide it. But here I'm showing you it, and you can reproduce it for when you come to look at this file. And also you can use it for similar situations where you want to reset a page back to what it was after some interaction with it. So now what we want to do is we want to generate 10 random samples of size 25. So we're generating sample means. So when we look at the spreadsheet on the next page, we're going to see 10 sample means, right? So now we're starting to build up this idea of sample means and sample means forming a distribution. So generating sample means for 10 random samples of size 25. The size can be altered. I'm just using 25 here. In fact, if I was doing it with students, I'd start off with a smaller sample size, but because of time constraints, let's just stick with 25 for the purposes of this. From a normal population with mean 100 and standard deviation 15. And when we look at the next page, in cell A1 on page 2.2, what I've done is, again, exploiting the syntax for TI-Nspire, the random normal command, mu, sigma, n, and they've all been assigned values. Mu is 100, sigma's 15, n is 25. And we've generated a cell formula equals the mean of those. And then what you do is you fill down to generate the sample means for 10 random samples of size 25. So when we go to this page, it's important now that students understand that these values here, these are all sample means, and you would expect them to be dancing around quite close, you know, not too far away from the population mean of 100, which again is anchored in cell B1. This quantity here is the mean of the sample means, and the fantastic, and this is what Frank showed, is that the theoretical considerations here is that the sample mean is denoted by x bar, and E of x bar, the expected value of x bar, is equal to mu, and it's the foundation for why you can perform sampling in this way, and Frank illustrated that quite nicely in the guise of proportions. And here's our sample standard deviation, and this is this currently mythical value of sigma on root n, which we end up talking about in theoretical considerations later. So again, we've got a similar setup. We've got a spreadsheet on the left-hand side, and we've listen spreadsheet application on the left-hand side, and a notes application there on the right-hand side. So you can control the sample size there if you wanted to. If we go to the next page, we can also control the sample size on this page. We also have a reset button. So these are our sample means, right? So these are our 10 sample means, and that's our mean of the sample means, and that's our population mean, if you know what I mean. So we could muck around with that for a little while. We go to the next page, and Frank made some really good remarks here about the normal probability plot. What it measures is departure from normality. So if your sample values are very close to that line, then the data is exhibiting reasonably good approximate normality. The closer those data points are to that line, the better, and the closer it is to a normal distribution. Frank gave a really good explanation for that plot. This one is not much going on here. It's a bit of a cricket's page, this one, but actually there's a program hiding behind it. It's the reset program again. So cutting to the chase now, this is where we want to generate S random samples of size n. Right, so we want to generate sample means for S random samples of size n, right, from a normal population, again with a mean of 100 and a standard deviation of 15. Now this is quite a complicated cell formula. It's best read from inside to out. So again, we've got rand norm mu sigma n. We're calculating the mean, so we've got sample means, and we're expressing those as a sequence. The sequence has to have a variable associated with it, so I've called it k, and basically this sequence goes from 1 to s. So in other words, we're controlling, s is the number of random samples. So if we go to the next page, you can see there that s is 200. So what we've got now in our spreadsheet, if I pressed Control 1 and then go down 1, we've got 200 sample means. Control 7 takes us back up to the top. So we've got 200 sample means. The sample size is 10, and what you'll notice here, the population mean is 100, and the mean of the sample means is 100.288, which is quite close to the population mean, and this is what you would expect it to be. And then what you're also seeing is an increasing closeness between the sample standard deviation and what we would expect from sigma on the square root of n. Frank made some really good remarks about the importance of the square root of n and the fact that it's a denominator. And so getting students to talk about, well, what happens when you increase the value of n? What does that do to the quantity, sigma on root n, for example? It's really important that students understand that. This command here, this is approx. This is just to make sure that we end up with a floating decimal point answer rather than a crazy sort of fractional answer. So pretty much the same thing being displayed in the notes application there. So if we press escape and then we go to the next page, this is where we've got 3 sliders. We've got the reset slider. In particular, we've got the sample size n, which is currently at 10, and we've got 200 samples. So, I mean, you could knock it back to 100 if you wanted to. The upshot here is you want students to notice what happens to all these sample means as n increases. And so when n increases, what you expect is you expect a scrunching effect, you expect the dispersion to decrease, and you expect the distribution of the sample means to behave in a more normal fashion. And so you can show that by clicking on the slider here for n equals 10. So we're expecting to see a scrunching. You'll also notice from those 2 vertical lines that the mean of the sample means should be dancing around but really close to the population mean. That's the foundation of this. So we're getting that scrunching effect. And basically, this is what's happening because the square root of n, we're increasing n and it's in the denominator. So that the standard deviation is decreasing. So that's a lovely demo. It can also be shown in the guise of a histogram and a normal PDF. And Frank showed you how to locate that and use that. So if we increase n here, we're expecting the distribution to look more normal. and we're also expecting to see a scrunching effect take place. While it's not part of this investigation, you can also look at the effect on number of samples as well, and that also comes out quite nicely. And it's good to show the random fluctuations as well when you're increasing n and you're increasing s. Here are three excerpts from some simulations, and basically what I want to quickly show you here is from a sample size of 25, we had a mean of the sample means of 100.23, and if we increase the sample size by a factor of 4, the mean in this instance got closer to the population mean of 100, but also notice that the standard deviation approximately halved, and that's that square root of 4 equals 2 factor coming into play. That's a much better illustration of normality. We've got a lot more data points, and what you'll notice in normal probability plots is that the departure occurs mostly, and not by much in this instance, at the end. So what you can do with students is you can, after going through the simulation, you can give them the definition. Now, I haven't got enough time to go through the theoretical considerations. I'll just show you that I would spend about 10 minutes talking through with the students, those results, but that won't be the part of tonight's webinar. So after doing that, if random variable capital X is a normally distributed random variable with mean, mu, and standard deviation sigma, then the distribution of the sample mean will also be normal, where E of X bar, now E of X bar is a random variable, and it's random variable for the sample means. So the expected value, or the mean of the sample means, is the population mean, and the standard deviation of X bar is equal to sigma on the square root of n. Now that's not so surprising when you're dealing with a starting distribution which is very close to normal, if not normal. But the power of this is in the central limit theorem, when the sampling distribution of the sample mean is not, well, if random variable capital X is not normally distributed. And I think that this is a lovely demonstration to finish. We look at a random variable capital X which has that probability density function. This is an example of the uniform distribution or rectangular distribution. So it's equal to a half from X values from 2 to 4 and 0 otherwise. Now, in general, that can be written as the definite integral from a to b of 1 on b minus a dx, and the mean is just a plus b on 2. So in other words, it's 2 plus 4 on 2, which is 3. The standard deviation is 1 on 2 root 3 by b minus a, and that's where you get the 1 on root 3 from. So in this instance, rather than generating from a normal distribution, we're generating from a non-normal distribution. So we're generating S random samples of size n from this uniform or rectangular distribution defined on the previous page, with a mean of 3 and standard deviation of 1 on root 3. In the column A formula cell on page 4.4, we've assigned the sample means to be a sequence, and it's the mean of 2 times rand n plus 2. The sequence is called K, and the sequence goes from 1 to S, and you've got control over the S value. Where does this 2 times rand n plus 2 come from? Well, on your calculator, random numbers lie between 0 and 1, and what we want is we want to draw numbers, random numbers between 2 and 4. So this is like a transformation. So if you consider the inequality rand n from 0 to 1, multiply through by 2, so you end up with 0 less than or equal to 2 rand n less than or equal to 2, and then add 2. to both sides, to both ends of the inequality, you end up with 2 less than 2 rand n plus 2 less than or equal to 4. So that's the basis for that formula. You could ask students to try and construct it. That would be a nice little activity. So again, we've got our listen spreadsheet on the left-hand side, and we've got our notes application on the right-hand side. We've got 200 samples of sample size 5, so it's a nice idea to have a low sample size, and the spreadsheet houses 200 sample means. Let's look at a picture of that. So remember, this starting distribution is uniform, and it's a great illustration of how powerful the central limit theorem is that when you increase the sample size, what should happen is you get that scrunching effect. It's that sigma on root n, but also as the sample size increases, the sample means end up behaving more normally, right? So taking on the properties and features of a normal distribution. And it happens quite quickly. As Frank was talking about in the textbooks there with sample proportions, approximate normality will occur for sample sizes around 25 or 30 or so. So I think it's really important to show students the central limit theorem from the point of view of starting with a distribution where random variable capital X is not normally distributed. And another distribution which would be really good to use would be the exponential distribution, because it's already got that skew. And what happens is that the central limit theorem basically smooths out that skew. The central limit theorem isn't mentioned, I don't think, specifically in the study design, which is puzzling, but I think students should know it, that when you let random variable capital X be any random variable with mean, mu, and standard deviation sigma, when n is large enough, so it's that fuzzy figure of about 25 or more, the distribution, and that'll depend upon, sometimes you need a bigger n value if your starting distribution, is further away from normality, if that makes sense. So when n is large enough, the distribution of the sample mean has an approximately normal distribution with an expected value for the sample means for the, of mu, and standard deviation of x bar is sigma on root n. So that completes my illustration of sampling distributions of sample means. In conclusion, I think it's really, really important to set up simulations, to go through it slowly with the students, and then back it up with the theoretical considerations which are illustrated here. The mathematics is quite straightforward, but it's really, really powerful and well worth your while going through it with students. So well done to Frank. Thanks very much, Brian, and pass it over to you to wind up.
Yeah, well done to both of you. I think both those presentations dovetailed together beautifully, and that has been reflected in accolades from attendees that I've been reading in the chat window there. So thanks, Peter, and thank you, Frank. Can I just point out that both of this evening's presenters were instrumental in developing a set of short videos, review videos for students. I've just swapped to my web screen here. The one that's on the page now is on notes and math boxes. That one is actually from the further maths review videos for students, but you see that there's a whole range of the topics there. Of course, we are so accustomed to going to, on the website, the teacher resource section, which is under here with all of the lesson plans. But it's also well worth taking a look, or at least directing your students to the student resource section, where exam preparation videos have been prepared, and as I said, from Peter and from Frank. and for Victoria, you can see we've got the further maths and the maths methods. I know a lot of students, rather than watch it from the website, prefer to go to YouTube. So, you know, this one here, efficient calculator use, this is on the notes pages. I put those links in the chat, so if you monitor back through the chat history, you can see the links to those. You will also get links to these pages in my closing PowerPoint notes. Just before I do close out, though, can I just quickly give a quick plug for our upcoming webinars, and particularly point out the Curriculum Inspiration series. These are short ones. These are only about 15 minutes long, and we're sending them out at 4 p.m. So 14th of August, that's next week, 4 p.m. Curriculum Inspiration on string patterns. You've got another one on 3rd of September. Just short ones. Our aim there was, at that time, thinking that we might be able to target into a staff meeting. So if your math staff are still at school at 4 p.m. on those days, that's something that you could tie into. Of course, all of the webinars can be watched on demand, and look at, there's a great history of them here, including the Curriculum Inspiration ones. The event that you saw this evening will be posted within the next couple of days and also available there in the on-demand and also on the YouTube channel. So once again, thank you to both of our presenters.
Thank you.
Now is your opportunity to type in any last-minute questions. I won't be able to answer them, but Peter and Frank may be able to. When I close the event, you will be taken to a page where we invite you for your feedback. Included in that, you might like to also list anything that you would like to see in future webinars. And you will be receiving an email within a couple of days giving you the links to both the recording and also the TI-Nspire files that you saw Peter and Frank demonstrate this evening. For anything else, stay tuned to the newsletter, link on your page here. And, of course, you can always phone directly through to the Texas Instruments office in Australia or New Zealand. So I'll close out with a final thank you for attending, and, of course, to our presenters, Peter and Frank. Good evening to all.
Good evening.
All right.